Take 3. One or more of your final exam problems will involve the following object. S is going to be the surface of this paraboloid, z equals 4 minus x squared minus y squared. Above the first octant, where x, y, and z are all positive. C is going to be the boundary of the surface S, where it's broken into these 3 pieces, C1, C2, and C3. So C1 is going to start at on the x-axis at 2, 0, 0, and go around through the xy plane to the point 0, 2, 0, and then follows on around, as you can see in the picture. So note that our boundary has the positive orientation that we want. It's going around the surface, and as we go around the boundary, the surface is on our left. Now that we have this surface, also we want to note that the surface S is one of 4 boundaries of a solid W. So we've got a solid, a surface, and the boundary of the solid, and this curve C, which is the boundary of the surface. So with this in play, we want to think about what kind of problems we might encounter that concern this object. If we go back to the beginning, where we started off with derivatives, this is calculus class after all. And the first thing we did was we started talking about derivatives, because that's the first thing we talk about in Calc 1. Actually, first thing after we do like limits and continuity. Once we do limits and continuity, we have the ability to talk about derivatives. So derivatives show up where we find equations of lines tangent to curves. We had to upgrade that because our functions don't describe curves. Our functions of 2 variables describe surfaces. So instead of equations of tangent lines, we want to find equations of tangent planes. One question we might ask here, given a point on the surface, find the equation of plane tangent to the surface. Derivatives, plug in point, we got that. If you notice some of the problems that showed up yesterday, one of them was that problem. So probably not on this one, but it's possible. It's possible. Also in the category of derivatives, we talked about vectors, and we wanted to combine vectors and derivatives, like some Calc 3 Reese's peanut butter cup. And so I could pick a point on the surface and ask about the gradient. I could the gradient being the steepest path up the surface. Think about this little hill. You can think about the steepest path up the hill. We could apply the dot product to the gradient and say, now that you've got the gradient at a point, I can pick some other direction and say, what is the rate of change of this function in that direction? So I could ask a directional derivative question. Moving on, the next big thing that we did was integration. One of the big challenges that we faced with integration was describing the stuff that we're trying to plug into our integral. So how could we describe this with, how could we describe this solid with a triple integral? How could I describe this volume with a double integral? Could we do that in use a double integral in polar coordinates? Could we set up a triple integral in spherical coordinates or cylindrical coordinates? So in the category of integration, we might just want to describe this object with double and triple integrals. Our most recent set of topics had us dealing with vector calculus, in which we had to spend a lot of time parameterizing stuff. so that we could integrate vector fields. So the other thing that we could see show up here is I could give you a vector field and ask you various questions about integrating that vector field. To that end, I have a couple of vector fields. So the things we want to think about are derivatives, so derivatives, including things like gradients and tangent plane, integrals, double and triple, and our alternative coordinates, and then vector calculus. With this last one, vector fields in mind, I do have a couple of vector fields in mind. So I wrote down a couple of vector fields. I wrote down these two vector fields. My original plan was to give you a choice. I was like, I'll pick one of these vector fields. But I want to give you a minute to think about what your choice is. And by a minute, I mean like a day. So what I want you to do is think about this surface, its boundary, the solid, and that this is one of four boundaries, 2. And I want you to think about these two vector fields. So think about describing this surface, describing the solid. What we could do to make that, to calculate using double and triple. What could we be calculating with double and triple integrals? And I want you to look at these two vector fields and decide which one would you pick. If you had to pick one of these vector fields, which one would you pick? And why? You can't just pick one at random. It's like one of those internet tests that says this, which house are you? And then it has you choose a bunch of stuff. And then it decides which Hogwarts house you should be sorted into. As if people don't just self-sort based on how they see themselves. You know what I mean? All right. So that's your task. One or more of your final exam problems most definitely involves this object, this surface, this boundary, and the solid that the surface contains. The other three boundaries are going to be the XZ plane, the YZ plane, and the XY plane. So those will be your other three boundaries. I want you to look at these two vector fields and decide which one you like more. One of these vector fields you should definitely prefer. I like this vector field more than the other one. They're probably both going to make an appearance. I haven't decided. I haven't made my final cuts on the final yet. But one of them you're going to like more. And I want to know why you like it more. You can't just like pick one at random. You got to know why you prefer this one, especially given this surface. Any questions? Vague and evocative questions. That's what I try to ask. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.